what is Mmana Gal? So it's a moment method antenna analyzer. It was originally introduced by MiniNEC, which is the longest cousin of EasyNEC. We're not going to get into the history. There are two versions. There is the professional version of Mmana Gal, and then there's the free version. And on this slide, I included a little bit of the comparison about what the difference is. The short version is that the basic version is a little slower and can't support as many elements to the antenna. So if you're trying to plan out some ridiculously complicated antenna that has like 45,000 different elements, you're going to need the professional version. And if you're designing an antenna that has 45,000 elements, you can probably afford the professional version. So bottom line is, I've never found anything in the basic, I've never found a limit in the basic version that wasn't good enough for me. And as far as I know, it is a Windows only program. I've never tried to install it on anything else, and I've never come across a version that wasn't for Windows. And I'll also say here, interrupt me with questions anytime you want. Please don't wait till the end, just speak up. So the takeaway from this slide is there's a free version and there's a pro version. So the next thing I'm going to talk a little bit about is how to get Mmana. Now, you would think that this would be a really simple process. If you're like most people, you would go out to Google and you'd type Mmana and you'd go find some download link and off you go. But the truth of it is, dang you, RJ. So the truth of it is that it can be a little bit confusing to find Mmana. For example, if you just Google it, you'll probably end up at this at the hamsoft.ca website, which you can't download the software from. The official website is this gal-ana.de, but even if you go there, you kind of have to follow a bunch of links to the basic version until you finally find the download link here. So I will put the actual page in the chat for anybody who wants to go get the software. And I may actually send out these slides after we're done as well, if anybody thinks it'll help. The bottom line is, getting your hands on the software is not as straightforward as you would think, and that's all this slide is really meant to talk about. Moving on. So what if you need help? Some people like instructions or destructions, depending how you look at it. So on that same link that I just posted in the Zoom chat, there's some pretty decent documentation that might help you if you have a really specific question. Really, the only way you're going to find the answer to your question in that document is if you already have a pretty good idea of what the answer is, and it'll help you confirm. It's kind of like reading any ham radio book. But I did have to look some things up in there when I was learning, so there is a little bit of instructions on that page. All right, now we're getting into the meat of it. The basics of the basics. So the reason I named the slide the way I did is because there are some very, very basic terms that you need to understand to get anywhere in this program. First and foremost, what is a wire? I mean, we all think we know what a wire is, but the reality is that in the software, a wire is any metallic part of the antenna, any conductive part of the antenna. And that could mean that it's a radiating element, it could mean it's a part of a counterpoise, ground plane. Any part of the antenna is a wire, end of story. And the software automatically determines whether a wire is a radiating element or some part of the counterpoise or grounding system. You don't tell the software, hey, this is the ground plane and this is the actual antenna. You don't get to do that. It figures that out. The next thing to understand is what the axes actually represent. Some of this should be obvious, but we're going to talk about it anyway. So when you're looking at the z-axis of the antenna, that's up and down. That's the floor to the ceiling. When we're talking about the x-axis, think of that like left to right. And when we're talking about the y-axis, think about stuff that's closer to you and stuff that's farther away. So how does this matter? Well, when you get into the software, you're going to find that there's some views like the XY view, the XZ view, and the YZ view, and what they mean. So the XY view is a top view that you're looking down on the antenna. The XZ is a side view, and the YZ is another side view. And when we open up the software, which is, I promise, coming in just like a couple of minutes, you're going to see what I mean. The next thing I'm going to give you in the basics of the basics is the metric system is your friend. One bad habit hams get into, especially older hams, is they start talking in feet, and this software is not going to help you if you start talking in feet and inches. Embrace meters. Bottom line, embrace meters. So what are we actually going to do today? We're going to do a tale of 3 basic antennas. I'm going to show, assuming there's enough time, I'm going to show how to design a basic quarter wave vertical antenna with a ground plane. We're going to do that at 2 meters. I'm going to show how to design a basic half wave dipole at 40 meters. And we might tinker a little bit around with off-center fed or a Wyndham antenna because it's a really easy thing to show you when we're looking at a half wave dipole. The advantage to an off-center fed antenna, if you don't know, is it is a way to get more than one band out of the same wire antenna. We're also going to talk a little bit about a half wave inverted V 20-meter antenna. And this is one of my very favorite antennas because a half wave inverted V at 20 meters can be built out of $3 worth of materials, hoist a painter's pole, and you can put it up camping. You don't need any fancy towers or balance or anything. It just works. I actually have talked to Slovenia on one of them for my front yard. So some of you might be asking, Mike, can I use Mmana to design beams and Yagis and slopers and J-poles? Yes. That is not what we're going to do today. My goal is to talk about enough to get you started so that you can try this on your own. And I'm happy if anybody wants to email me questions after they get going. All right, this is actually the last slide that matters. We're almost through the slides. We're going to talk about what the basic procedure is to design an antenna. And I'm going to try to keep this slide up on the video while I'm demoing the software so everybody can follow along the procedure. But these are the 5 basic steps to designing an antenna. I'm not going to go through them right now because you're going to see it in the software. So let's do a demo. Let's see if I can remember how to use Zoom well enough to do this, because Zoom is a pain in the neck. All right, here we go. When you open up the Mmana Gal software, hey RJ, give me a thumbs up if you're seeing it. Okay, and then I'm hoping that you all can still potentially read the slide in the video, but if not, that's okay. I'll read it to you. Yeah, you might just have to make it bigger, RJ, but that's okay. So when you first open the software, this is what it's going to look like. You're going to have these 4 tabs: geometry view, calculate, and far field plots. And while this software works pretty well, it can be a bit overwhelming because there's all these fields and boxes where you can change values. And the nice thing is you're going to find that 98% of the time, you don't need to change any of them. So don't be scared away by all these fields that maybe make no sense. You could probably teach a semester course on this program in college if you wanted to cover everything that it can do. We're just trying to get people started. So if we try to design we're going to start with the dipole, because a basic half wave dipole is one of the simplest antennas in the world. And we're just going to start with a basic, what did I say? A 40-meter half-wave dipole. So the very first thing that you want to do is give your antenna a name. So we're going to say 40-meter half-wave dipole. Now, if it's 40 meters, does anybody know what frequency that should probably be built on? I'm going to make somebody tell me.
7 megahertz.
Say that again.
$7.260.
Jack says 7.260. Okay, Jack, that's what we're going to go with. That is kind of the upper half of 40 meters, but that's fine for what we're trying to demonstrate. So according to my procedure, all you need to do on the geometry tab is name your antenna and set the frequency that you're designing for. We're done with the geometry tab. All these other fields, I don't need to worry about that right now. So the next thing you're going to do, it may feel like what you should do is click on this like view tab, which we can, but all we're seeing in this view tab is empty space. We're just seeing empty space. And there's no antenna here. So what we want to do is we want to click the wire edit button, which is a little obscured, but it's this little button right here. And if you hold your mouse over it without clicking, it'll say wire edit. If you do that, it's going to open up this whole new window, and this is the wire editor. And let's just give you guys a really, really brief tour of the wire editor. There's these three buttons over here. The first button, the one that's selected, is edit wire. The next one is new wire. And the next button is running off the screen. So it actually represents new loop. So really all it is the ability to draw a box instead of an individual wire. If you use the new loop, what you're going to get are 4 wires connected in a square, or polygon, more accurately. I've never actually used the new loop button because I've never tried to design an antenna in the software that had a closed box. The next thing that you're going to look at down here is these projection buttons. You have 3D, which is what we're in now, XY, XZ, and YZ. So just a quick reminder, Y means you're looking down on the antenna. XZ means looking at one side of the antenna, and YZ means you're looking at another side of the antenna from about a 90-degree turn. You kind of have to visualize the free space. You have a zoom slider where you can make things bigger and smaller. And that's about all you really need to worry about for the basics. So what we want to do is draw our antenna. Because we're drawing a 40-meter half-wave dipole, we need the best view to do that in is XY. Okay, we just want to look down on the antenna. So imagine you're in a drone looking down on your dipole. Now, one thing that might be tempting to do in this view is to draw it up in the air, because that's where antennas go, up in the air, right? But you need to understand that this is not where you control the height of your antenna. You're just designing the antenna. We'll deal with where it is later. So the first thing we're going to do is go click on this little button for new wire. We're going to go out here and we're just going to draw a wire. So now you see this red wire, which may actually be a little bit hard to see on the screen share. So let me know if it is. But you see this red wire. And up here on the right, we're seeing the characteristics of our wire. And the first thing that we notice about this wire is that it's 50 meters long. A 50-meter long wire isn't going to work for a half-wave 40-meter dipole. We need it to be like 20 meters long, right? And the seasoned hams, I'm always going to pick on Arnie, are going to be like a half-wave 40-meter dipole is not 20 meters long. Yeah, that's okay. We'll let the software help us with that, right? So I'm gonna click on this wire and I'm gonna right click on it. It's gonna bring up this menu. and I'm going to go to wire definition. That's what we care about, wire definition. And the only thing we're going to change in this window, we can change all kinds of stuff. Where we can change whether or not it's connected to other wires, whether or not it's a lambda segment. We can change its location and free space. The only thing we care about right now is the length. We're going to make it 20 meters long. Boom. Now our wire is 20 meters long. That's half of 40 meters, halfway. We're done. That's all there is to a dipole. It's a wire, right? Now, one thing somebody might say is, but wait a minute, a dipole is actually two wires. One goes this way and one goes this way. But remember, to the software, that's just where you're putting the feed point. It doesn't care if it's two wires. So we're done. We're done in the wire editor. That's all we had to do was draw our 20-meter long wire. We're going to hit OK. And that took us back here. We want to click on this view tab. And now we have a three-dimensional view of our complicated antenna, which is just a wire in free space. Now, the next thing we have to do is we have to tell the software how we're going to feed this antenna. So the way you do that is you right-click on your wire in the View tab, and we're going to say Add Source to the center of the wire, because it's a dipole, that's where we want it to be. And you'll see this little red circle showed up, and now we have a complete dipole. We're done in this tab. We don't need to be in the View tab anymore. We're going to go over to the Calculate tab. Remember that 7.26 frequency that Jack gave us. A couple things we want to change here. First of all, the antenna is asking us, what kind of ground do you want to talk about? Free space? Nope. We need a real ground here. Dipoles don't work without the earth. It's better when it's far away, but they don't work without the earth. We can also talk about a perfect ground. This is what it means. It means that there's no dielectric constant to the soil. There's no moisture. You know, this is perfection. Well, that's not going to do us a lot of good. We need something real. So we're going to choose the real ground. I've never designed an antenna in the software other than using real ground. You probably need to be an electrical engineer if you really want to get outside of that, because you're not going to have very good luck making an antenna that actually works in the real world. There are also some, if you click this button where it says ground setup, you can actually set things like the conductivity of the soil, the dielectric constant, and, you know, RJ has actually, I don't know if it was him or Paula, they actually kind of went and got their soil tested, and they actually know what this stuff is supposed to be. You can do the same thing, but for the most part, this has some pretty good defaults dialed in that'll work in most cases. I just leave it alone.
So how do you tell, you know, the conductivity? I know it's poor in Wyoming, but how did you get it tested to tell what it is?
We actually didn't test it. We've talked about testing it. We actually just went and got some reference material and went off of that. It's been a long time. I can look it up and send it out to the group sometime.
Okay,
No,
so
it's okay, but it's just, you know, in my informal testing, you know, when I was in Seattle and we had, I would hook and unhook radials and it didn't make any difference. And here, I don't think I could put enough radials down to improve my situation.
So I'm gonna be honest with you. This isn't something that I know a lot about, but again, there may be scenarios where looking that up or having your soil tested could help you design a more perfect antenna in the software. For the sake of this presentation, we're going to leave the software defaults here. The next thing that we need to decide on is what the height of our antenna is going to be. For now, one thing I want to be very clear to everyone about is you can't set the height to 0. That isn't because the antenna won't work. Vertical antenna will work just fine sitting on the ground, but the software just won't accept it being all the way on the ground. So your minimum is like 0.1 meters. So now imagine we have this 20-meter long piece of wire that's 10 centimeters off the ground. And if you know anything about dipoles, you know that's not going to work. But let's just see what happens. The next thing that happens is you're going to choose the material of your wire. We're going to use copper. You actually can control things like the wire diameter. We're going to come back to that at the end. For the sake of argument, this thing is going to use a wire that is 0.8 millimeters in diameter, which is a pretty thin wire conceptually, but we're just going to leave it at that. Now that we've set a frequency, our ground, height, and a material, notice this little button down here is not grayed out anymore. If you forget to add a feedback to your antenna, that is the most common reason why the start button will be grayed out. It won't let you model your antenna. We're going to go ahead and hit start, and we have some problems. First and foremost, it's telling us that our SWR is 1,271. Anybody want to guess why?
How about the ground? Also the length.
So it's not the length, because we know at 20 meters we're close. But what about the ground? What about the ground length?
Yeah, you're too close to it.
Yeah, there you go. You're right. So we need to get this antenna up in the air a little bit. Dipoles don't work on the ground. So let's go 3 meters, which is about 10 feet up in the air, and we'll model this again. Now we have a 3.4 SWR. With a tuner, that's a usable antenna. It's also a cloud burner. At only 10 feet off the ground, most of the energy coming off that dipole is going straight up, and we can prove it. If we go over here to this far field plots tab, this is actually plotting what our antenna looks like. What you're seeing on the left is a top view, and what you're seeing on the right is a side view. It's the XZ view. And there's a couple things. Number one, this is a mostly omnidirectional antenna, meaning that from an azimuth perspective, it's pointed almost every direction equally, but most of the energy is going straight up, right? We don't see gain from the antenna until we're at like 32 degrees upward angle, right? And we're seeing like 8 dB of straight up, right? Good NVIS antenna, not a very good HF antenna, right? You can also click this 3D far field button down here and get a 3-dimensional view of the lobes of power that would come off of this antenna. Okay, great. Now we see what the antenna we've designed will do. But some of you might be thinking, I still know that 20 meter long is wrong for a meter dipole. So let's make it better. We can go back to the calculate tab and we can look at this and go, okay, we're getting an SWR of 3.4. I wonder where this antenna really is resonant. So we come down to the bottom, the plots button, and it's going to bring up this window, which I'll make a little bigger. Oh, I guess I can't make it bigger. I'm sorry. And what we can do is what we care about for this particular exercise is our SWR. And we can click a detailed button, and we can actually see our SWR plotted out. And it looks like our lowest SWR is right about what? 7.27. Well, we don't have to guess, right? We don't have to guess. We can actually close the button back, go back in. Sorry, I have to model the antenna again. One thing you're going to find is every time you want to do something different, you have to model the antenna again. So I'm going to go ahead and do that, model the antenna again. a new result, go back into plots. And this time I'm going to choose SWR, but instead of clicking the detail button, I'm going to click the resonance button. And it's going to say, hey, are you good with writing the current frequency to the gain tables? And of course we are. So what this is showing us is our point of resonance is 7.26. Wait a minute, that's what we designed it for, right? So one of the problems that we're running into here is we have an antenna with a 3.4 SWR that is resonant exactly where we wanted it to be. And that's because Jack, when he told us 7.26, he based that off of 20 meters, a 20-meter long antenna. So what if we made the antenna a little taller? Instead of 3 meters, we could go 10 meters. And we start to see that SWR come down. And this is always, in my experience, my limited antenna experience, that just happens with dipoles. That the impedance corrects itself as you get higher and higher. So now we have an antenna that's, what, basically 30 feet off the ground. And if we go look at our plots, it's still a cloud burner. It's getting better though. Okay, you know what we're not going to do right now? We're not going to try to design the world's best half-wave 40-meter dipole. I'm trying to teach you guys how to use the software. You can perfect the antennas yourself. So let's move on to the next antenna type and try this exercise a little different. So the next one that we're going to do is the 20-meter inverted V. So I'm just going to go ahead and click this little new button up here at the top, which is going to clear everything out, and we get to start over. Because building a dipole is easy. You draw one wire. It starts to get more complicated when you have more than one wire, like you do with an inverted V. So first thing we want to do, right back to the beginning of our procedure, is we want to name our antennas. So this is going to be a 20-meter inverted V. And really, we could leave this frequency, and we just will. We'll just say 14.15 is the frequency we want to build this antenna for. So we're done. We named it. We set the frequency. Hopefully, I'm not putting everybody to sleep. And again, we need to go into the wire edit menu up here at the top. Just remember that button, wire edit. So we're going to start out similarly to how we did with the dipole. We're going to put ourselves in the XZ view. That way we can actually see up and down and the side view of the antenna. Very important, we want to be in the XZ view. We're going to do the button for a new wire, and just like we did with the dipole, right along the x-axis, we're going to draw ourselves a single wire with the center even with the z-axis. We look in here, the software made this thing 20 meters long. That's too long for 20 meters. So what we're going to do is we're going to go back into wire definition just like we did the last time. We're going to go ahead and set it to 10 meters long to get in the ballpark. And then we're going to zoom in a little bit because this is not an inverted V. So what I'm going to do is I'm going to click on this wire. I'm going to tell it, divide the wire into 3 pieces. And you might be thinking, well, an inverted V is basically 2 wires. Why do you need 3? We're going to get to that. So we divide the wire into 3 pieces. Now we have 3 wires. And I'm going to change my tool over here on the side to the edit wire instead of new wires. I don't need to draw any new wires. Right? We're going to zoom in a little bit more with the slider. And this middle segment, I'm going to make it smaller. In fact, I'm actually going to make it like 10 centimeters long, really short. And imagine this is your feed point, right? So we're going to right click, we're going to go to wire definition, and you can tell because it's red that the center wire is the one we have selected. That's how you know. Now, this is really important. We're going to change the length of this wire. but we still want it to stay in the middle. So we want to make sure that we're keeping the middle point. This middle point button is selected. That's really important. We're going to change the length here to 0.1 meters, which is 10 centimeters. Boom. Now we have this really, really short wire in the middle and these longer wires off to the side. The next thing we're going to do is we're going to take that, we're going to probably have to zoom in a little bit more so we can grab it. We're going to select the middle of that middle wire, and we're just going to start moving it up the Z-axis. And an ideal inverted V is usually going to have about a 45-degree angle. Okay. Now, a couple things are going on here. One, our middle isn't in the middle anymore. We got to fix that. The second thing is, as we move this up, we're making these two elements of our antenna longer, right? They should have been around 5 meters each before, but now they're more like 6 meters. So we kind of need to pull them in a little bit.
Hey, Sean,
Yeah, go ahead.
is there like an undo? Like, so if I grab something wrong and it got me all cattywampus, can you?
There's no undo.
Yeah, so my life just stinks.
Yeah, one thing you'll get in the habit of with this software is save often.
Got it.
There is no undo button. Yeah. So somehow we got all cattywampus, as a matter of fact.
Hit undo.
There is no undo, so you can't do that. We're just gonna do it this way. Right? So again, it's very important for an inverted V to be symmetrical, right? Let's go. Why does it keep doing that? I've never actually had one of these do this before. That is a new one on me. So what we're going to do is this. We can actually start over really fast. Draw a new wire. Make sure it's in the middle. And I apologize for having to start over. That's okay. It's not a big deal. Again, we want this to be about 10 meters long. We're going to divide it into 3 pieces. We're going to take the middle piece. We're going to set it to a really, really short length, like 10 centimeters. And then we're going to take it and drag it up. And so now our wires are around 6 meters each, so they need to be shorter. So what we're going to do is we're going to pull them in. And hopefully this thing doesn't do the same thing it did before, because I actually don't understand why it did that. So now that's 5.8 meters. That one's 5.9. So what we're going to do now is I'm going to zoom in enough that I can recenter that centerpiece. I just zoomed in more and it gave me a more precise grid. Now it's in the center. This element is 5.9 meters and this element is 5.9 meters. And this antenna is not the right length to be a 20-meter inverted V, but that's okay. We're in the ballpark. Maybe we're down to 5.6 meters. We're in the general ballpark. Okay. Now we have an inverted V. We're done. We know the lengths are wrong. We're close enough. Who cares? We hit OK. Now we can see our antenna 3D in free space, right? Does anybody remember the next thing we have to do?
You need a feed.
Need a feed point. Good job, Mark. So when you're in this view, not the wire editor, but when you're in this three-dimensional view tab, if you hold the shift key down and you drag with your mouse, you can drag the antenna around like this. And if you let go of the shift key and drag your mouse, then you actually get to change your view angle, tumble this thing all over the place. So I'm going to use the shift key and I'm going to move this down a little bit. So the feed point area is right in the middle of the screen. So I can zoom in. I'm going to do it again. So I can zoom in until I can click on that middle wire. You see how it's a little darker than the others? That's how you know it's selected. We're going to right click on that guy, add source to the center of the wire, right? And then it changes your zoom again. But you can now see with the little red dot that we now have a feed point in the middle of the wire. Okay, we're done here. We can go over to the calculate page, and one thing about this antenna, let's talk a little bit about height. Okay, the height that you set in the calculate tab, when you say add height, that is height below the lowest point of the antenna, right? So if we go look at our antenna, and the feed point wire is selected right now, right? We can go over here down wire number 2 and see that that point is 4 meters off the ground, right? So the highest point of the antenna is 4 meters higher than the lowest point of the antenna. But any height we add to the antenna is being added to the bottom of the antenna. So you've got 4 meters here, and we've got 10 meters here, which means the highest point of that antenna is actually 14 meters off the ground. We don't need it to be that high. We can set this to 1 meter. So by setting the height to 1 meter, that means that the ends of the wires at the bottom of the antenna are 1 meter off the ground, about your waist height, right? And that highest point of the antenna is 5 meters off the ground. 4 meters in the antenna and 1 meter that we're adding on. If you're taking a 20-meter inverted V like this and you just want to take it camping or something and throw it over a tree limb, you don't need it to be any higher than that. It will work. So we have it 1 meter off the ground. We set the frequency to 14.15. At this point, we can model the antenna. We have an SWR of 13. Hey, Mark, why is our SWR so high?
Well, I'm gonna guess length, but that didn't work the last time, so I'm kind of out on a limb here.
Yeah, so
I'm at least 5 meters off the ground on this limb. So yeah, you're gonna have to give me a pole to get off this limb with.
so you nailed it, right? This time it is length, right? We know our inverted V is too long, right? We drew it too long. Now we have a choice. We can go back into the wire editor, we can correct the length manually, or we can let the software do it for us. So let me show you how to do that. We want to go into the plots menu, and we need to figure out where this antenna that's too long is actually resonant. We know it's probably, because it's too long, it's probably going to be somewhere below 14 megahertz, right? So we go over here to SWR, but this time, instead of clicking detailed, we're going to click resonance. Tell it yes. This antenna is actually resonant at 12.746 megahertz, right? 12.746. I need somebody to remember that number.
You did better than I did. Mine came in at 10.4.
Oh, well, you made it way too long. So 12.746 megahertz. Who can remember that? I need somebody to jot it down.
Got it.
Okay, 12.746. So what we're going to do is we want this antenna to be resonant at 14.15. So we're going to make the software fix it for us. Close this menu. We're going to go all the way back to the geometry tab, and we're going to change this. What was the number again?
12.476.
476. We're going to basically tell the software that we designed it to be that long by changing it on the geometry tab. Then we're going to go back to calculate. We're going to remodel the antenna by clicking the start button. Now we have an SWR of 2.74, which still isn't great, but that's okay for the sake of argument, right? We can go back to plots. We can go back to SWR and hit resonance again just to check our work. And sure enough, 12.748, we're at the resonant point of the antenna. But we want it to be resonant 14.15. So there's this button up here on the bar that kind of looks like a square within a square. And if you mouse over it, it says wire scale. I'm going to click that button. Okay, what do you want the new frequency to be? Well, we want it to be 14.15 megahertz. And then it's asking you, what am I allowed to change to get you there? Can I change the x-axis? Can I change the y-axis? Can I change the z-axis? Can I taper the wires? Can I change the radius of the wires? Can I add height? What are all the things that you're willing to let me change to achieve this? Well, we don't want to taper the wires. We don't want to change the size of the wire because this is the wire we have. But we don't want to change the height of the antenna because if we make it taller, we're not going to be able to get it over that tree limb when we're camping. So the only thing we're willing to change are the length of the elements, X, Y, and Z axis, and we hit OK. And weirdly enough, it looks like it did nothing. No feedback that, hey, I did what you asked, right? But if we hit the start button again, now this antenna is resonant at 2.68, or now the SWR is 2.68. And if we go over to our view, we zoom out and we look at our wires, I'm going to get rid of the currents. And I click on these wires, that's now 3.5 meters. It's not 5.6 anymore. And that's 3.5 meters. The software corrected the length of the wires to achieve the frequency we wanted. We have an SWR of 2.6, which is still arguably too high, but it's manageable. Most radios with a built-in tuner would be able to use this antenna. And if we go look at our far field plots, we have a cloud burner, but it's still putting out, positive gain as low as 33 degrees. That antenna would work for HF. You'd lose a lot of your power straight up, but it would work. Now, similarly, an inverted V, much like a dipole, if you put it a little higher in the air, it'll do better. If we change 1 meter to 3 meters and we remodel our antenna, that actually made the SWR a little worse. But remember, we're changing, when you change the height of a horizontal antenna, you will change the feed point impedance. And we can prove it because this is our feed point impedance column right here. And what happened is, by changing the height of the antenna, we changed the feed point impedance from -33 to -53 ohms. And when we say -33 to -53, that means off of the 50 ohms that we already told the software we wanted it to be. Right? So he's telling you I'm now 53 ohms out from 50 ohms. So this thing's actually, off by that much. So what we can do is before we do that, let's actually go a little higher. Let's make it 10 meters high. Now our SWR is way off, all over the place. We're now 30 feet in the air, which means the tippy top of our antenna is 34 meters in the air. This is way up there. But what we can do is the same thing we did before. We can go to plots, go to SWR, hit resonance. And now we find this antenna is resonant at 14.85. Okay, so 14.855. We're going to do the same thing again. We're going to go back to geometry. We're going to set this to 14.855. Go back to calculate, remodel the antenna. Look at that, 1.48 SWR. That's not bad. We're going to go up to wire scale, change this back to 14.15, hit OK. Now we have an inverted V 30 feet in the air that has a SWR of 1.48 at 14.15 megahertz. The other thing you notice is now that we got this antenna up in the air, we're very much starting to change the shape of the lobes coming off this antenna. Because horizontal antennas, the higher you get them off the ground, the better off they do. Now, okay, so we know it does 1.48 SWR at 14.15. What if we want to see what the SWR is across the rest of the 20-meter band? You could sit here and randomly enter frequencies, or you can go down here to plots, go to SWR, and you can hit the detailed button, and it'll give you a nice sweep. Right now, this view is showing us the entire 20-meter band, all the way from 14 megahertz to 14.3 megahertz, 3.5 or whatever. And we're under 1.75 across the entire 20-meter band. There's a lot of hams that would say that's not bad. And if you sat here and you tinkered with it long enough, you could achieve the mystical one-to-one match. Any questions so far? Are you guys all drinking from a fire hose and I lose you?
I think we are,
Yeah,
but that's all right. We're learning.
yeah.
You're
Just
not
play with
alone.
it. Yep, yep. I gotta start somewhere.
So antennas are voodoo magic. Don't feel bad. The ARRL publishes a book that's like 3 inches thick that they call the antenna book.
So, Sean, this is really interesting. I'm really glad you're doing this for the group. I've been using 4NEC2, NEC, 4NEC2. I don't know why it's called that. And it has some interesting features to it. I think obviously a lot of similarity. I don't know what the basis of its calculations are, but generally I've been pretty happy with it. This one's probably easier when it comes to generating the antennas. And I assume that you can handle loading coils and that sort of
Yeah, it's a good,
capacitance hats and those kinds of options.
so I'm not going to get too deep into loading coils, but I will show you where you do that. So back on the geometry tab, one thing you'll notice about this software is there's a bit of a shorthand to this software, right? Each one of these wires has a number. So you have wire 1, wire 2, which is that feed point wire, and wire 3. So our feed point is in wire 2. You agree? And it's at the center of wire 2. Make sense? So that's what you see here, where we're telling it we have a source that's in wire 2 center. So there's a part in this software you have to learn kind of this shorthand. Well, similarly, you can come down here and tell it use loads, and you can add a load somewhere like W2 and see if I can remember the actual shorthand. I never can. But essentially what you do then is you add a load to a wire segment using the shorthand. You set a type, and then you go ahead and set the induction or the resistance and the capacitance or the impedance of your loading coil. One thing the software will not do is calculate what the load should be for you. There's all kinds of websites out there that will help you calculate what a 40-meter trap should be or what a 10-meter trap should be. But all you have to do is punch in here the microhenries and the microfarad of capacity, and you will get your trap.
Yeah, that's interesting. One advantage of the 4NEC2 is it'll do optimizations. You get close to things like length and height and load, and you say, okay, now optimize for SWR and gain or front to back ratio, and you just turn it to loose. You can proportion against all of those, or select one thing that you want to do an optimization for, and then it'll go through and it'll modify whatever you selected, lengths and heights and loading, which is pretty nice. I wish 4NEC2 were as easy to work with as this one is in terms of setup. But
Well-
yeah, I find it interesting that I won't do any calculations for you for
Well,
loads and the like.
And I think why I latched onto this software was it may be harder to do some things, but it's the most intuitive of all of them that I tried. One thing I will show you is up under the tools menu, there is an optimization section that will do some of this. I have never succeeded in using it. If you go into the advanced menu, there actually is a, so what you're talking about is here. I've never figured out how to use it.
Yeah, cool. It's good to see that they've got an optimization section. Yeah, and when I do the 4NEC2, I'm using optimization all the time, and it works pretty cool. I'm going to start playing around with it. If I can figure out optimization, I'll let you know.
Okay.
May take me a while, but if I get that far, I'll sure let you know.
So the last antenna that I was going to design for everybody was a vertical, a 2-meter vertical. We're an hour into this. Who wants to, does the repetition help? Do you guys want to see me walk through a vertical, a ground plane vertical? Okay. That's
Can you
one.
just pull up a file that you've already done?
Actually, yeah, I can.
I'd be okay with that.
And we can do it that way. So here's the 2-meter vertical, quarter wave vertical. And this is the completed vertical with radials at a 45-degree angle. Each radial is a half wave. Now, one thing that you're not going to get to see because we didn't build the antenna is that at no point did you tell the antenna which part is a radial and which part is a radiating element. It figures that out on its own. The other thing that you'll notice is that these radials sit below the XY boundary, which means if you don't add some height to this antenna, these radials are underground and you're going to get all kinds of weird calculations. But if we go over to calculate, I built this antenna for right at 146 megahertz, 10 meters in the air. So again, this antenna is 30 feet in the air. If we go ahead and run our calculation, we get an SWR of 1.2 at 146 megahertz. And our far field plots look like this. And we can actually go look at our 3D plot. And this is a really nice 2-meter vertical antenna. Nice. This would be a good repeater antenna. Has a really nice 6.4 dB of gain at 3 degrees. This antenna just shoots straight out the side in every direction. The reason why this antenna has such a low takeoff angle is the height. If we drop this thing down to more like 10 feet in the air, we go look at our plots, not nice. It's not quite as nice anymore. And this is a really good way to demonstrate to hands. This was good for me as a new ham. It was good for me to understand how height really helps an antenna. There's a guy who used to be a member of the Shyway Club, a guy by the name of Jim Abel. And I worked with him at Dish. And Jim used to have a saying that you want as much metal as high up as you can get. Arnie's laughing and nodding. But even at 10 feet in the air, this antenna is offering you 40 dB of gain at 7 degrees. So those of you that put a 2-meter antenna up on your house, 10, 15 feet in the air, that's why it works so well.
Hey, Sean,
Yeah.
really quick. You don't even have to walk through it on the screen. I am still playing with the dipole, and I'm trying to optimize, and I'm missing a step. I'm going the wrong direction.
Okay.
So,
Do you want to share your screen?
I've got it on a different computer, so I cannot.
Got it.
So I go to plots, I go to SWR resonance, and it's telling me that the resonant frequency is 18.847.
Okay.
So
So-
now,
So now take that, go back to the geometry tab and enter again.
okay.
So go back to
Uh,
the geometry tab, go to frequency and punch in that 18.847.
yep, got that.
Then
Go-
go back to calculate and hit start, and you should see that resonant SWR pop up.
Yep.
Then what you want to do is scale.
So I go to the scale button up top.
The wire scale button, and it should show you your old frequency is 18.847. So now you want to enter the new frequency of whatever you want it to be.
Okay.
Let it change the axes, but don't let it change anything else, and hit OK.
Okay. I
and
was
now
not.
hit-
I got it. I was not going back to the geometry tab to change the frequency.
Yeah, don't you love how intuitive that is?
Yeah,
I,
that's
I learned that in the deep dark bowels of some random YouTube